All right, welcome back everyone to 1.7. In this video, we're going to be creating this precise definition of a limit, and we're going to do this through a couple steps. First, we're going to think about it graphically and think about what would be a good definition for a limit, a good precise definition. And then we're going to talk a little bit about it, from an algebraic viewpoint. There's going to be more equations and inequalities and things like this that we'll have to manipulate. So let's think about it graphically, right? Back in the days of 1.5, we said statements along the lines, right? If x is close to a, then f of x is close to L. Remember, f of x is probably not equal to L, but it gets very, very close to L. So using this idea, I would like to give you this definition, which is kind of the graphical limit idea. It's not quite precise, but it's heading in the right general direction, right? So it's going to push us in the right direction. So, okay, we say that the limit of f of x is L as x approaches a, which we know we have this nice notation for, this limit as x goes to a of f of x is equal to L, if we can make f of x and L as close as you would like. Like I said, a little wishy-washy, right? But it's heading in the right direction. So we can make f of x and L as close as you would like. Remember, probably not equal to each other, but very, very close to one another, by making x close enough to the value a, right? X is supposed to be approaching a. Okay, let's use this to solve some examples where we actually get a graph, right? And so, okay, this first one, I'm going to notice, or we could verify really using the direct substitution, that the limit as x goes to 3 for this function, the square root of x plus 1, right? Basically, if you were to just plug in 3 everywhere you saw an x, you'd have 4. Square root of 4 is 2. So as we would probably guess using our intuition, that this limit should equal 2. All right, I would like to use this app and try to verify that this definition kind of makes sense, right? So I would like to use this app to determine how close does x need to be to 3 so that our f of x is within distance 1/2 from 2. So already this is a little bit confusing. Let me show you the graph and maybe we can make more sense of what does it mean for the function to be within distance 1/2 from 2, right? Because this is saying that I want f of x and L, 2 in this case, to be close to each other, within distance 1/2 from each other. All right, so if you click on this link, it should bring you to this page right here. So we have our nice function, the square root of x plus 1. We can see as x gets closer to 3, the y value here, the function seems to be approaching 2. And I want to make sure that we can get the function within distance 1/2 from 2. And I want to know, what do we have to restrict? How far, I guess, can x be away from 3? Or how close do we really need x to 3 to make that happen? So, okay. If I go ahead and click on this right here, you can see some bands kind of pop up. And you can see actually that these bands are all the places, all the y values that are distance 1/2 away from 2. So you can go up to 2.5 or down to 1.5. But these are all the places that are distance 1/2 away from 2. And notice that I can mess with this, right? I can change this, I can make it smaller, I can make it bigger. So this right here is kind of telling me my bandwidth. So I want all the places that are distance 1/2 away from 2. So the claim is, if I restrict down my x values, I can make sure that the function lives in this bandwidth right here. And so I'm going to go ahead, I have one more kind of button to click here. And this is saying a distance that x is away from 3. So right, if I say that this distance is 1 for right now, you can see you can go all the way down to 2 and all the way up to 4. So if x is within distance 1 from 3, right, if I make it close enough, x and 3, in general are a value. So if I make it within distance 1 from 3, you can see that the function's values, all this right here, stays within this nice band. And this is the place, all of the y values that are distance 1/2 or less away from 2. So in this case, going back here, again, how close does x need to be to 3? Well, within distance 1 works. So I'm going to go ahead and just write within distance 1 from 3. So again, you can go all the way down to 2, all the way up to 4, but notice when you're in this range from 2 to 4, so long as we're within distance 1 from 3, our function's values are less than a half away from 2. Now, there are certainly values that don't work, right? There are many other values that do work, right? I can kind of extend this. This would also be fine, 1.25. But if I keep going, notice that, let's just make this a nice even 2, I suppose. This would be a case where I'm letting x move too much, right? So if I said x needed to be within distance 2 from 3, I could go all the way down to 2 and all the way up to 5. But all the way down here at 1, you can see, distance 2 away from 3, all the way down here at 1, you can see that the function's values are actually more than distance 1/2 away from 2. Right? They're kind of outside of this nice green band of goodness. All right. So distance 1 away from 3 works. Actually, even distance like 1.5 away works, or distance 0.5 away works, but distance 2 is too much. Okay, so again, we were able to make f of x and its limit 2 within distance 1/2 from each other. Well, what if you would like something a little bit closer, right? So this is kind of close. Let's make them even closer to each other. So in this next example, I would like them to be within distance 1/100th away from each other, right? So f of x and 2 are 1/100th away from each other. And again, because the limit exists, we should be able to find how close does x need to be to 3 to keep our function and 2 only distance 1/100th away. So let's go back to this app, the same one here. Oops, right over here. And now I'm going to change this bandwidth here. And I'm going to bring it down to 1/100th. Let's see if I can get it. There we go. 1/100th, very close indeed. So I'm going to go ahead and zoom in a bunch. So we want to make sure that we can keep our function within 1/100th away from its supposed limit 2. And okay, let's go ahead and restrict down this value here. This is changing the purple width. Oops, that's too far. All right, so let's start at 5/100ths. We can see at this point it's a little bit too much, right? It doesn't keep the function within distance 1/100th away from 2. It kind of breaks out of this good zone. So what if I go ahead and restrict it down? I'm going to do 0.4. That's pretty darn close. Just to be safe though, let me do 0.03. But again, there are multiple correct answers. Within distance 0.02 would be a good one, or 0.01 would be a good one, right? But so long as I stay pretty darn close to 3, the claim is the function is very, very close to its limit 2. Okay, so in this case, if x is within 3/100ths away, so within distance 0.03 from 3. So again, that's how close x needs to be to its a value, 3, so that the function is within distance 1/100th from 2. And the claim is, if this limit truly exists, then no matter how close you would like, right, whether that would be 1/2 or 1/100th or 1/1,000,000th or 1/1,000,000,000th or whatever, we should be able to find some distance. So long as x is close enough to that a value, within that distance from the a value, well, the function should be as close as you'd like to L. Okay, so this is graphically what we are doing. I would like to kind of switch over now to the algebra mode, right? In the last video, we did a lot of absolute value inequalities work because the claim is these things, these closeness, right, between x and a and f of x and L, right, these have something to do with absolute values. All right, so I'd like to go back to this other problem that I had, but now using algebra, determine how close does x need to be to 3 so that f of x is within distance 1/2 from 2. Okay, so let's talk about the second bit right here. I would like f of x and 2 to be within distance 1/2. Well, we learned from our absolute value inequalities, right? If you want the distance between f of x and 2, well, this has something to do with absolute value of f of x minus 2. We would like this distance to be less than 1/2. Within distance 1/2, so less than distance 1/2 away. And the question becomes, how close does x need to be to 3? So I'm going to do the absolute value of x minus 3. This tells me something about the distance between x and 3, and I want to know how small of a distance do I need, right? So I don't know what this value is, but I'm going to make it less than some distance. For now, I'm going to call this a d value, right? So I want to know what is this d value, so that if x and 3 are that close together, within distance d from each other, then f of x minus 2 is within, right, f of x and 2 are within distance 1/2 from each other. And now notice that this is actually very close to a problem that we solved at the end of our first video here on 1.7. Okay, so let's go ahead and break this down a little bit. Last time, right, again, we're trying to figure out this distance that x can be away from 3, so we drew out a number line, right, just to kind of start visualizing this stuff a little bit. Ooh, my computer, live. There we go. It is alive. All right, so if I draw a number line here, the question is, how far can x move away from 3 and still have this inequality satisfied? Well, let's go ahead and substitute in, right? We have a very specific f of x. It's the square root of x plus 1. And staring at this, it may be hard to kind of get a distance statement from this thing. And so let's go ahead and use that nice theorem that tells us how to rip apart absolute value inequalities, right? And that's going to go negative 1/2 is less than square root of x plus 1 minus 2, which is less than positive 1/2. And we're going to go ahead and rearrange this and try to solve for x. So if I add 2 to both sides, well, 2 to all sides, notice this is going to get the square root bit all by itself. On the right-hand side, we're going to have 5/2. On the left-hand side, we're going to have 3/2. Again, adding 2 to all sides. Now I'm going to go ahead and square all sides. So I'll get 9/4 is less than x plus 1 is less than 25/4. Remember, whenever you're messing with inequalities, you have to be a little bit paranoid that something that you've done should have made the inequalities flip. And the claim is squaring, so long as everything's positive, doesn't make the inequalities flip. So we're actually okay. One last step, let's go ahead and subtract 1 from all sides, and that's going to give me, what, 21/4 over here. We're going to get 5/4 down here, and just so we know, this is equal to 1.25, and this is equal to 5.25. Okay, let's go ahead now and draw out our second number line. This says we want, right, if f of x and 2 should be within distance 1/2 from each other, then x should be somewhere between 1.25 and 5.25. So here's 4, here's 5, 5.25. There's 2, there's 1, that's a little too far, so 1.25. So notice, anywhere between 1.25 and 5.25, this is where we want our x values to be. This is what's required if we would like f of x and 2 to be within distance 1/2 from each other. So the question is, how far can x travel away from 3, or how really close does x need to be to 3? Well, a distance of 1 would be fine. We go down to 2, up to 4, that would be fine. We could actually go all the way down to 1.5 or up to 4.5, so this would be a distance of 1.5 away from 3. We could even go all the way down to 1.75, remember, because this is strictly less than that distance. And likewise go all the way up to 4.75. So that's maybe the best value here. D equaling 1.75 is good, but also anything smaller than that. D equaling 1.5, D equaling 1, D equaling 0.5, whatever. But as soon as you go a little bit beyond that, let's just say 2, right? So if I do distance 2, that would take me from 3 down to 1, and it would take me to 3 up to 5. So if you're within distance 2 away from 3, notice if you could guarantee that you're on the right-hand side, right, with all those big numbers, 5 and so on, you'd be fine. But actually you can't guarantee this, right? You might be on the small side, you might be on the big side. So if you just know that you're within distance 2 away from 3, well, you could be down here at 1, and that'd be a problem, right? Because you want to make sure that you're in this zone between 1.25 and 5.25 in order for this to work out. So d equaling 2 would not be a good value. But like I said, there are multiple good values. D equaling 1.75 is good, 1.5, 1, all that stuff, they all work out. And really quick, let's go back and connect this with the graph. So if I bring up this app again, reset for the one where I want to be within distance 1/2 away from 2, notice that my d value of 1 works out nicely, 1.5 works out nicely, 1.75 just barely does it. You can see that they're basically right on top of each other right here, but 1.75 barely works. But as soon as you go a little bit farther than that, as soon as you do 1.8 or 1.9 or 1 or 2, right? Anything like this, notice that the function's value is sometimes just a little bit too far away from that 2, right? It's too far away. All right, so that is now the algebra that connects this kind of graphical idea. So now that we have this all done, we've kind of seen the algebra in a specific case, I would like to introduce the precise definition of a limit. With all the bells and whistles, all of the technicalities, what exactly is this precise definition of a limit? So to start off, right, all these words, right, we need the function to be defined on some open interval that contains the number a, right? You got to be able to approach from the left and the right. This is a two-sided limit after all. Except possibly at a. Remember, limits don't really care about what's happening at a, they only care about what's happening around a. Then we say that the limit of f of x as x approaches a is L, and we have this nice notation which we've brought up several times now, if the following is true. All right, and here's how it goes, right? We want that if x is close enough to a, so I'm going to go ahead and start writing here, if x is close enough to a. The way we measure closeness is with the absolute value, so it's within some distance away. Then f of x should be as close as we would like to that L value. And here's where it becomes a little bit technical. So we want to say as close as we want. So we can't specify, a number like 1/100th or 1/1000th or 1/1,000,000th or 1/1,000,000,000th or anything like this. It's got to be kind of arbitrary. It's an arbitrary small number. It's whatever you would like. So I'm going to say for any small number that's positive, right? So we're going to say epsilon that's greater than 0, the Greek letter epsilon. So let's say I want them within distance epsilon away from each other. Then again, we should be able to go out and find a distance that x can travel away from a and still have this inequality be good. So that is to say there's some other distance. There is a delta which is greater than 0. Again, it's a distance. So that so long as x and a are within distance delta from each other, then f of x and L are within that specified, right? We wanted them as close as we wanted, some epsilon value, they're within epsilon from each other. So this right here is the formal definition of the limit, and it's like, oh my goodness, right? How do I use this darn thing? Well, that's what the next video is going to be all about. So I'll see you guys in a minute.